Swayam Prabha. Digital India. Educated India.
Welcome to the course on Introduction to Micromachining. We are going to discuss in this particular course. First, I will tell you what micromanufacturing is, and after talking about the micromanufacturing, I will take you to micromachining. As we all know, it is a highly competitive world, and a country can be economic leader only when it is at forefront in research and development activities. If you go 50 years back or 45 years back, Japan was the economic leader of the world. The main reason being that they were spending lot of money on R&D activities. They were able to spend 95% of the total R&D activities expenses of Asia, and Japan alone was doing that. Microfabrication is going to witness an excellence and research and development at a remarkable rate in the near future. And before I start this course on micromachining, I would like to advise all of you that if you want to achieve the ambitious goals of your life, be honest, sincere, hardworking, and have the junoon towards your work. What is fabrication? First, let us understand what is fabrication. It is building of machines, structures, or process equipment by cutting, shaping, and assembling components made from raw material. We will discuss in very brief about micro cutting and micro shaping, but not assembling of micro components in this particular course. Now, fabrication can be classified in different ways depending upon the size of the components being fabricated. You can classify them as macro, meso, micro, and nano fabrications, but here we will be mainly concentrating on the micro fabrication. So, micro fabrication, as you can see here, can be classified into process of fabrication of structures that are measurable and observable. They are visible by the naked eye, and dimensions of these features or equipments is greater than or equal to 1 millimeter, then only we classify them as macro or meso fabrication depending upon the dimensions. But if dimensions are less than 1 millimeter, then we classify them as micro fabrication. So, micro fabrication is the process of fabrication of miniature structures of micrometer size. It needs microscopic equipment to view them, because the size of the features or the component is so small that you cannot see them by the naked eye. So, you need the help of external devices normally known as microscope, and the dimensions of these features or the equipment is greater than 999 nanometer or less than or equal to 999 micrometer, then only we put them in the class of micro fabrication. if it is less than 1 micrometer, then we classify them as nanofabrication rather than microfabrication. Here I will limit my discussion mostly in the area of microfabrication rather than nanofabrications. Here in this particular course I will be ignoring meso and nanofabrication both. Now, when we want to define micromanufacturing, we can define it as a set of processes used to fabricate features, components or systems with dimensions most conveniently described in micrometers, as I have already mentioned to you, that is less than 1 millimeter, but equal to or greater than 1 micrometer. Now, question arises why we want to go for miniaturization or microfabrication. We should look into it. Advantages: when we are having the micro devices or equipment, then we are able to minimize the energy required for operating those devices. Also, the material required in the manufacturing of all these devices. Once we are minimizing the material requirement and use of energy, that indirectly means that we are reducing the power budget. Also, the fabrication of such devices is not that simple, but these devices are faster devices. They have increased selectivity and sensitivity. They give improved accuracy and reliability, and the cost performance advantages are there, and integration with electronics simplifying system becomes easier. Now, here this slide shows you the dimensions of different parts which we come across in everyday life. If you see here, in this one, paper thickness which we normally use is approximately 100 micrometers, and it also includes the human hair. They are also around 100 micrometer in dimension, especially the diameter. 8 micrometers are the red blood cells, also the capillaries, they are around 8 micrometer in size. 0.5 micrometers includes the visible light, and also the machining tolerances in many cases are 0.5 micrometer. 0.5 micrometer, or you can say 500 nanometer, and 0.07 micrometers will start, this has already started production of ICs in terms of 0.07 micrometers or 70 nanometers or more than that. And if you see here in the last one, 0.0003 micrometers, that is around 0.3 nanometer, is the atomic spacing in solids. 0.3 nanometer, or you can say also in terms of microns, 0.3 nanometer or angstrom, 3 angstrom. Now, what are the various methods of micro manufacturing? In general, if you see, you can deposit the material over the substrate and create the micro features or micro devices. You can remove the material from the bulk material, and then you can create the micro features or micro devices. You can use the forming processes also for creating the micro features or devices. You can use joining processes, and you can also use the casting processes. Now, if you see various kinds of material deposition processes, they are given here. Electrochemical spark deposition, we will discuss all these processes later on in detail. Second is electro discharge deposition process, chemical vapor deposition process, that is also known as CVD, then physical vapor deposition processes, that is known as PVD, then rapid prototyping, rapid tooling, and then there is a process called LIGA. All these processes are in the category of material deposition processes, with the help of which we can create micro devices. Then there is another category that is known as material removal processes. Here you have a bulk material like this, and then you keep removing the material from here and create a micro or nano features or micro or nano devices. It has two basic classes. One is first one is the traditional material removal processes, and second is the advanced material removal processes. We will concentrate later on our whole discussion and whole course related to these two particular micro material removal processes. Then there is the third category known as forming or shaping processes. They are known as rolling, forging, extrusion and drawing, and sheet metal working. Then there is a class of welding processes. This welding process has various kinds of processes, just like arc welding, gas welding, resistance welding, and so on. Then you have a brazing process, and then there is a soldering process also. So, we are not going to discuss that, but brief introduction I will give you. And then you have the casting process. In the casting process, as you may be knowing, that you are melting the material, pouring it into the mold, and then letting it solidify to get the desired shape and size of the component. We are not going to discuss in detail in this particular course about casting also. So, microfabrication is going to witness an excellence in R&D, that is research and development activities, at a remarkable rate. Now, micromachining methods, as we have seen already, they are classified in two classes. One is known as traditional micromachining methods, another is known as advanced micromachining methods. So, in traditional micromachining methods, we include micro turning, micro milling, micro drilling, micro grinding, and so on. There are various other processes also which can be included in traditional micro machining processes. Then there is another class of micro machining method, that is known as advanced micro machining processes or advanced micro machining methods, which can be further classified into three classes. One is mechanical, thermal, and chemical. Under the mechanical, there are various processes where mechanical force is being used to remove the material from the bulk material and then create shape and size of the features or create the devices, definitely in the dimensions that is less than 1 millimeter. It includes micro AJM process, that is the micro abrasive jet machining process. Second one is the micro ultrasonic machining process. Third, micro abrasive water jet machining process. There are other processes also which can be included in this category. I have not listed all of them. Then when we are talking of mechanical type of micro machining processes or nano machining processes, there is another class which is known as nano finishing processes. That means, here rather than creating a feature or creating a device, what you are doing is you are changing the texture, you are changing the surface finish of the surface, rather than a particular point, whole surface is being covered, and in these processes abrasive particles are used. So, we will discuss in detail all these processes where we are changing the surface texture and surface finish of the surface to be used, and it includes the processes like abrasive flow machining, magnetic abrasive finishing MAF, magneto-rheological abrasive flow finishing process, that is known as MRAF, then magnetic float polishing, it should be MFP rather than MPF, MFP, magnetic float polishing. Here is this particular process is used for finishing of the spherical surfaces rather than flat or 3D surfaces, for which all other processes are being used. Now, in these processes of mechanical type of machining, micro machining processes, mechanical force is being used to remove the material. But there is another category where thermal energy is being used for removing the material by melting and vaporizing. Here material is being melted and vaporized, and these processes are known as thermal micro machining processes, which includes micro EDM, that is micro electric discharge machining, and second is known as micro electron beam machining, third is known as micro laser beam machining, and then micro plasma arc machining. In all these processes, heat is generated, intense heat is generated in a very localized area. As a result of that, the base material or the workpiece material melts and part of it gets vaporized, and the molten material is removed from the workpiece surface, so that the feature is created over there. We will discuss all these processes in greater detail later on. And then there is the next category, that is known as chemical and electrochemical micro machining processes, which includes electrochemical micro machining processes ECMM, and next is known as photochemical micro machining processes. So, we will discuss these processes also in detail later on. Now, what happens if we see all these traditional and advanced micro machining processes? In many cases, they are not able to satisfy the requirements of the components or the features that you are creating. Something or other happens, or in some cases you will find that the material removal rate is quite low. So, it is going to take lot of time. As a result of this, engineers, scientists, they have developed the hybrid micro machining processes. Hybrid micro machining processes means two or more than two micro machining processes are combined together and a new process is formed, which takes over the disadvantages of the component processes or individual processes and makes use of merits of these component processes, and that is what is known as hybrid micro machining processes. As we see, micro electrochemical spark machining process, EDM, this is the combination of electrochemical machining process here and micro EDM process. That because micro EDM process has its disadvantages, we will discuss in greater detail later on, just like it creates thermal cracks, it gives residual stresses, or recast layer is deposited, while in case of chemical, corrosion may take place. So, by combining these two processes, we are able to take or make use of their merits and remove some of the demerits. So, that is what we will discuss in electrochemical spark machining process. Same way, micro electrochemical grinding. Now, if you see the grinding process as such, which is the traditional micro grinding process that you can see here. So, we try to take the advantage of grinding process and electrochemical machining process and try to avoid the disadvantages of both of these processes, and that is how we have electrochemical micro grinding process. Same way you have the micro electric discharge grinding process. Again we are trying to take away the disadvantages of grinding process and EDM process and have micro electric discharge grinding process. And there is another process called as ELID, electrolytic in process dressing, where you have the electrochemical machining process and grinding process combined together and try to take the advantages of all these processes later on, we will see. Then you have methods of microfabrication using material deposition, just like what I have already told you, like vapor deposition, chemical vapor deposition, physical vapor deposition. Then thermal energy is being used like electro discharge deposition, electrochemical spark deposition, and then there is a very extensively used area that is known as rapid prototyping or rapid tooling or layered manufacturing or additive manufacturing. Many names has been given to this. Anyway, we are not going to discuss this particular process, because here you are depositing the material rather than machining, and then there is a process called Liga process. So, all these are the microfabrication processes, but we are not going to discuss them because we are concentrating ourselves on the machining processes rather than deposition processes. Micro products nowadays focus is on miniaturization through development of novel production concepts, especially micro and nano concepts for the processing of non-ceramic materials. So, microfabrication deals with all kinds of manufacturing processes, but at micro nano level. So, we will be discussing these processes separately in detail. The replication of micro parts through molding is one of the preferred routes for micro manufacture because of its mass production capability and relatively low cost. Because whatever processes we are going to discuss, there you can create the feature or the parts individually, but when we talk of molding process, there you can make the micro features, micro parts much more easily compared to micro machining processes, because this process is applicable for mass production. But when we have production in small numbers, then these particular processes cannot be used, then we have to go for micro machining processes only. However, in this series of the lectures, I will mainly concentrate on microatricious processes or micro machining processes rather than micro deposition or micro mass containing processes, because this molding, casting, etc., they come under the category of mass containing processes. Now, material removal processes, as I have already introduced this, there are two classes. One is for creating the features, another is for changing or improving the surface. So, you have micro nano machining and micro nano finishing processes. Again, in two classes, traditional machining processes and advanced machining processes. Same way you have traditional finishing processes and advanced finishing processes. Let us see what is the definition of the word micro machining. It is made up of two letters, rather two words, micro plus machining, which simply means removal of material at micro level. Here components, you can have macro components, but material removal is at micro nano level, or you can have micro nano components and material removal again is at micro nano level. The devices which are normally made by this process are known as MEMS, micro electromechanical systems, NEMS, nano electromechanical systems. You can see here in this figure, it is a 2 millimeter by 2 millimeter picture, which is showing the leg of a house fly, and you can see how many different components are captured in 2 by 2 millimeter frame. Now, this can tell you the size of these components and the features that have been created in these components with the help of micro machining processes. Unfortunately, the present day notion is machining of highly miniature components with miniature features is known as micro machining, which is wrong. Literally, it should not be so. The correct definition of micromachining is material removal at micro nano level with no constraint on the size of the component. This simply means that size of the component can be of micron size or macro size or meso size, but the removal of the material from the component to create features or the component itself should be at micro level, then only you can call it as micro machining process. Now, classification of micro machining processes, as we have seen in the earlier slides, micro machining methods, they can be classified in traditional micro machining methods and advanced micro machining methods, and we have already seen all these different types of the processes. So, I am not going to repeat them. These are the hybrid processes which also we have already discussed. Now, micro nano finishing processes I have already explained to you to some extent, like grinding, lapping and honing. In these processes, all these processes are nano, micro, nano finishing processes where surfaces are being created, and on the right hand side advanced machining processes are there where features are being created, and we can see abrasive flow machining, magnetic abrasive finishing, magnetorheological finishing, chemomechanical polishing, magnetorheological abrasive flow finishing, electrolytic in process dressing and magnetic float polishing. All these are the finishing processes which are going to create the surface finish of micro nano level RA value. In some of the cases, these processes have been used to create surface roughness which is lower than even 1 nanometer RA value. We will discuss them. Now, I have already told you MAF means magnetic abrasive finishing process, AFM means abrasive flow machining process, MRF magnetorheological finishing, CMP chemomechanical polishing and MRF magnetorheological abrasive flow finishing process. Then comes the ELID electrolytic in process dressing and magnetic float polishing process, where this is the only process which is used for finishing spherical surfaces like ball. Now, here are the some examples of the parts, or you can say micro features created into different types of the parts. You can clearly see here, these are the micro features created which are shown here in the enlarged view. This is laser cut stain like pattern in miniature stainless steel tube with 1.25 millimeter outer diameter of the tube, and features created are most of them less than 1 millimeter in size. And here you can see another example, laser drilled hole. These are the holes of 15 micrometer as the size, pattern in polyurethane tube. There are certain problems in micro machining, especially when you are using traditional micro machining processes. Mechanical deformation takes place, because all these traditional micro machining processes, namely micro turning, micro milling, micro drilling and so on, you are using mechanical force to remove the material in the form of the micro nano chips, and because the tool that you are using is of very small size, of micron size. So, because of these mechanical forces, the deformation of the tool takes place, or in some cases you can say may take place, and because of which the accuracy of the parts will be affected. Other processes, thermal deformation, it comes in the processes where heat is generated, and this is true in both cases, traditional micro machining processes as well as advanced micro machining processes. In traditional micro machining processes, when you are removing the material, definitely forces are being used, and whenever and wherever you are using the forces to remove the material, some part of the energy is converted into the heat energy, and that heat energy deforms the material, the part being machined or the feature being created on that particular part. And in advanced machining processes, there is a group of advanced machining processes, namely laser beam micromachining, electric discharge micromachining, plasma arc micromachining, and so on, where the mechanism is material removal by melting and vaporization. And because of very high temperature, the thermal deformation of the micro parts takes place, which again affects the accuracy of the part being machined. Then there is surface integrity, which means the surface finish, damage to the part in terms of micro nano cracks, texture of the machined surface, all are considered in case of surface integrity, and they are affected according to the type of the process, like whether it is a traditional machining process or advanced machining process. In advanced machining process also depends upon which category of advanced machining process you are using, which will affect in a different fashion the surface integrity of the machine feature. Then gap between the tool and workpiece, how much gap you are maintaining in case of advanced machining processes, that affect the performance and the quality of the part being machined. Even in case of traditional machining processes, to some extent it has effect. Then you have coordinate shift in tool handling, as I will show you in the figure. Here you can see on the machine tool making, this is perfectly machined, but here there is a off centering, as you can see here between this and this there is off centering, and this will affect the accuracy of the part being machined. Here it is a tilting of the axis of the tool holder, just like as you can see here. So, there is a tilt this much, and it will affect the accuracy of the part being machined. And then tool and spindle handle as a set, there is a shift of the axis of the tool from the main axis or of the coordinate system. So, all these is going to affect the quality of the surface being machined or the feature being created. Now, what I will do? I will give you in brief an overview of traditional abrasive finishing processes. One of them, traditional abrasive finishing processes, one of them includes grinding process, which all of you know it, and it is being the finishing process which uses abrasive wheels or tool made of abrasive grains retained by bonding material. It is more efficient, but difficult to achieve the desired fine finish by grinding alone, because abrasive particles are being used, and those size of those abrasive particles is not exactly the same, it varies, and more importantly the protrusion of these abrasive particles is different at different locations of the grinding wheel, and it affects the depth of the material being machined, and which affects in different ways. We will discuss them later in detail. Then there is a lapping process. In this lapping process, a low pressure abrading process used for obtaining surface finish and dimensional accuracy superior to the grinding and honing process. Here there is no direct contact between the lap and the workpiece, rather it is through the liquid. We will see it later on. The material is removed by applying loose abrasive slurry between the work and the lap. This is very important. Abrasive particles are loose, they are floating in the fluid, not abrasive particles are not bonded in the grinding wheel as in case of grinding or honing process. So, definitely the quality of the surface being generated here is different from other two processes, that is grinding and honing. And then third is the low velocity abrasive finishing process characterized by low cutting pressure and large area of contact. It is generally employed to improve the accuracy of internal cylindrical surfaces. This is also very important process and commonly used in the industries. Process capabilities, as we can see here, certain traditional machining or finishing processes capabilities are being given. You can see precision turning. In case of precision turning, you can see here, this is the kind of the surface texture created on the machined surface, and the surface roughness height of micro irregularities obtained in case of micro turning varies from 1.25 to 12.5 micrometer, which is very large. In case of grinding, you can see again this kind of the texture is being obtained. It depends upon the distribution of the abrasive particles on the grinding wheel, and there is a lot of overlap of one peak over the other. So, texture obtained is not exactly the same as shown over here, but something of this kind, and the peak of the micro irregularities varies from 0.90 to 5 micrometer, which is substantially lower than what you get in case of precision turning. And in case of honing, as you can see here, texture is more or less the same as in case of grinding, but the height of micro irregularities varies between 0.13 to 1.25 micron, which is quite lower or much lower than your grinding process. And in case of lapping, as I told you, their abrasive particles are not abrasive particles in case of lapping are freely flowing inside the fluid, and you can see the kind of the surface finish you can obtain, and here the height of micro irregularities varies from 0.08 to 0.25 microns, which is much lower than all these processes, and it is very highly finishing process. And super finishing, as you can see here, it is still better than lapping process, and you can see the main important thing is to see more or less the flat surface you are able to obtain, except that at some places you are having the cavities, and the surface height of micro irregularities is 0.01 micron to 0.25 micron. So, you can see in all these traditional finishing processes, super finishing gives you the best surface characteristics compared to all other processes. And all note it carefully that all these processes are based on mechanical force, and which leads to the shearing and indentation, and you get this kind of the surface finish. Then lapping process, you can see here, it is shown, you can clearly see that this is the surface originally obtained, and then you have the lap over there, and this is the lap, and in between you have the fluid, which is not visible because this is the highly enlarged picture, and there are the abrasive particles in the fluid. Now, you can see here, this is the actual schematic diagram. Lap position and pressure control can be done with the help of this, and here is the workpiece, and guide rail is there for this, and when between these two you will have the fluid and the abrasive particles, and when you rotate this, as you can see here, this is the rotating direction. As it rotates there, the fluid also rotates and abrasive particles get in contact with the workpiece, and they are removing the material in a very small amount, because penetration depth is low, because force is not very large, compressive force is not large. So, depth of penetration is small. Important thing to note is that here this part is rotating in the clockwise direction, while this bottom part, which is holding the workpiece, is rotating in the anti-clockwise direction, and the revolutions per minute of both of them are different, and that makes the process quite interesting. Here abrasive particles are embedded in the lap. Lap usually made of cast iron, copper, leather or cloth. Dimensional tolerance, you can see here, obtained are 0.4 micron, and surface finish obtained is as good as 0.025 to 0.1 micrometer. Now, lapping force you can see here, this is the abrasive particles and this is the workpiece and it is in the pad. Now, you can see here when this abrasive particle comes in contact with the workpiece, then very small load is working over there and it is able to remove a small amount of material from this particular workpiece. So, you can see clearly an abrasive particle is embedded in the rigid pad which supports the particle load, and the normal force is normally 0.01 Newton on a particle is significant to cause the surface indentation and scratching. In such a small force, so penetration is also very small and final surface finish that you are obtaining is quite good. Now, but there is another process known as MRF process, magnetorheological finishing process, and in this process you can see abrasive particles are suspended in the gap between the workpiece and the MR fluid is there, in the fluid they are suspended, and whenever there is a relative motion between the abrasive particle and the workpiece, the material is being removed. So, particle or surface contact area is very small, the hydrostatic pressure results in insignificant normal force, that is 10 raised to power minus 7 Newton. The buoyant force is also too small to cause appreciable surface indentation. That is why you get very good surface finish in case of MRF process, and this surface finish can be few nanometer only. With such a small magnitude of force, the depth of indentation will be in nanometer, leading to nano level surface finish. Honing is the process as mentioned earlier for finishing cylindrical surfaces, and you can see here this is the spindle and here is the nano abrating bronze guide is there, and this is the stone where you have the embedded abrasive particles. Honing tool consists of a set of aluminum oxide or silicon carbide bonded abrasive particles, and this stone is called, this is known as stone, which is holding these kind of abrasive particles. In case of super finishing, in place of as we have seen in case of honing process, here there is slight difference. Here the cylindrical surface is there, but you have the rotation of this cylindrical surface and oscillation of this surface also there. So, that this stone is also reciprocating and workpiece is rotating, and because of this relative motion between the two and abrasive particles embedded in the stone, you get very fine surface finish after finishing process. Now, if you see the side figure, there is slight difference between the two. Here you have the two cylinders, and this is known as centerless micro honing. In this particular case, you have these two cylinders, and since these two cylinders are rotating, so because of that friction, this workpiece is also rotating, and on the top of it you can find the whole stone which is reciprocating, and so you have the relative motion in the circular direction as well as the axial direction, and because of this relative motion between the abrasive particle and the workpiece surface, you get very fine honed surface. Mechanism of material removal in micro nano machining. Now, this is the general process, say like a boring process. You can see the material is being removed in the form of the microchips over here, and this is a broaching tool, this is the micro broaching, and this is the workpiece, and you can see these are the micro chips which are being produced and material is being removed. Accordingly, you will get the surface finish. However, these days lot of work is going on in the direction of molecular dynamic simulation of micro nano machining to understand actually what is happening during micro nano machining. So, there are certain groups of researchers who are working in India, like Dr. Prabhat Ranjan, Dr. Bala Subramaniam, etc. at Bhava Atomic Research Center, and other places also people are working to understand the mechanism of material removal in micro nano machining. So, in this particular case, forces acting on the workpiece are in case of micro Newton, and penetration is somewhere in case of in such cases as nanometer level, and that is why finally you get nano level surface roughness value. You can see here these are the chips. Overview of advanced abrasive finishing processes. Why advanced abrasive finishing processes? Why we need them? So, there are certain reasons why we should go for advanced nano finishing processes, while we already had some traditional finishing processes. One of the reasons being that complex geometrical shapes cannot be finished by traditional finishing processes. I will give you some examples later on, that in those workpieces you cannot use traditional finishing processes at all. So, you have to go for advanced finishing processes. Second thing is, traditional finishing processes, they are labor intensive in nature, just like grinding, honing, lapping, super finishing, etc. Hence, we have to go for advanced abrasive finishing processes. Thirdly, there are difficulties in controlling abrasive forces. Now, as you have seen already that in grinding, lapping, honing, etc., you have the abrading forces, and it is very difficult to control exactly what is going to be there with the forces during finishing process. Hence, the surface finish obtained is not very uniform, and it is not of the level in some cases which we desire in real life. And then nanometer surface finish requirements are there in certain cases, just like a sub nano level finish is required in case of optics, mirrors, which are used for aerospace industries or space industries. We need very high level of surface roughness value, just like even less than 1 nanometer. In those cases, we have to go for advanced abrasive finishing process rather than traditional finishing processes. And different surface finish in different areas of part, just like knee joint, there are certain components or devices where we need different surface finish. Component may be the same, but the locations are different, and at different locations we need different kind of the surface finish. So, in those cases we cannot go for traditional finishing processes, rather we have to go for advanced finishing processes. That is why there are certain areas in the advanced industries where we have no other alternative except to go for advanced abrasive finishing processes. These are the advanced abrasive finishing processes which I have already mentioned to you, like magnetic abrasive finishing, abrasive flow finishing, magnetorheological abrasive flow finishing, magnetorheological finishing, chemomechanical polishing, and magnetic float polishing, which is used for spherical parts. Now, there is another process, chemomechanical magnetorheological abrasive flow finishing process, which was developed by one of the student at IIT Kanpur, and the beauty of this process is that IIT Kanpur student was able to achieve the surface roughness value on the single crystal silicon wafer of the order of 0.45 nanometer, which is 4.5 angstrom. So, such kind of surface finish you can obtain only with the help of advanced abrasive finishing process in detail later on.